So this is the order. Okay, everybody. So welcome back. So I heard a lot of people were excited after last Monday, and we are continue. Hope you get even more excited today. So as last week, we have a lightning presentation. This is in TED style. You can see the list of professors here, and we have, in fact, a little change from the website. Dikai will give the first one. As you can see, it's already over there. So it's in Davos style. So we are going to be very strict. Everybody has 5 minutes. We leave all the questions to the end. And we will have food and drink outside. So after the question-answer period, we are going to meet the professors individually. OK, so let's welcome Dikai.
OK, before I start, let me first also welcome you, because I'm the Computer Science Department's seminar coordinator. So I will be regularly arranging and hosting the entire seminar series, not only the lightning ones. And again, I want to repeat the invitation from last week that it's not only professors that necessarily give these seminars. It's very good training for you guys. So if you've got something cool that you're working on, please talk with me. And we can discuss a way for you to give a seminar about your coolest research ever. And it's a great place to interchange ideas and so forth. Also, I have, as Yang Chang kindly mentioned already, I was one of the faculty guinea pigs who gave these 5-minute presentations at the Davos meetings. And so rather than, I'm just going to take advantage of that, because it's been already neatly edited. Can we switch back to my presentation? Into a 5-minute video by the World Economic Forum. And there's no way that I can possibly do better than that. So I thought probably the best thing that we can do is just to play that directly. In this era, when everybody's buzzing about big data science, I'd like to also ask you a more humanistic question. What makes language language? And what makes music music? Because language and music not only share common evolutionary origins and neurobiological processing, but they're also pretty much the only thing we humans do better than all other species. Scientific and humanitarian reasons led me to develop the world's first automated translation services in the early days of the web, because language are trade routes. Language lets us trade ideas, overcome barriers, share common ground. But it remains one of the hardest challenges in big data science. How do we learn complex relations between languages? Humans learn by seeing this round orange thing while hearing mama say, "qiu," "ti-qiu." And we correlate the Chinese we hear against a second representation of the environment we see. Over many instances, we gradually learn "qiu" means the round thing, "ti" means kick. Our robots today aren't good enough to do this. But when I first got to HKUST many years ago, I noticed Hong Kong requires all government proceedings to be kept in both English and Chinese. And this led to the idea that we could approximate the picture by hearing Mama speak Chinese while seeing an English representation of that environment. So the key question becomes, what kind of models can learn the relationships between any two natural languages? And attacking that problem gets us closer to identifying the universal DNA of language. Because language is what lets us think complex thoughts. And those thoughts let us create new languages with which to think more complex thoughts. In the great cycle of intelligence, language structures thought. Now, the traditional way linguists and mathematicians have thought of modeling language is, tell me if that sentence is grammatical. But this would not have done your average caveman very much good. What's really needed to survive evolution is to translate, "Look out, a tiger's attacking from behind you," into another visual or abstract representation that lets you decide quickly to run. But learning traditional translation models has exponential complexity. In attacking that problem, I was inspired by a long-standing scientific mystery. Why do languages across the world universally limit a verb's semantic roles to a maximum of 4. I discovered inversion translation grammars give rise mathematically to this magic number 4 in order to keep languages learnable. Because languages evolved to make translation easy to learn. Because otherwise, your tribe became dinner. Translatability is what makes language language. And learning translations is the main cognitive capability underlying intelligence. Even within this magic number 4 limit, all sorts of powerful translations can be efficiently learned. The same principles apply to learning relationships for all sorts of languages, visual languages, gestural and abstract languages, and especially musical language, because music and language share common origins. Music is the evolutionary foundation of language. And what makes music music is, again, the complex relationships between the many different languages of music, to which we've begun applying our translation learning models. Because it's not enough to master one of these. You have to learn to translate lyrics to melodies, melodies to chord progressions, to dynamics, to rhythm. Here, we're applying our translation model to learning lyrics, specifically challenge and response lyrics in hip-hop. The machine starts with zero knowledge, not even pronunciation dictionaries, and learns to translate any given challenge into an improvised, creative response. And we said, why stop with English? Let's do this for French. Notice all the complex relations that have to be learned. The response has to be somehow meaningfully related to the challenge. It should rhyme. Its rhythm should match to the challenge. Music, like other languages, forms trade routes to stimulate cross-cultural relations, just like the spice, tea, and silk routes did. Music is also one of the easiest ways to learn languages and to build relationships. We are building technologies that learn and technologies that help people learn. Technologies that build relationships and technologies that help people build relationships. The trade routes of language are one of the most important infrastructure investments needed today. And we have a long way to go, because the machines today still have a lot of trouble translating even what a 2-year-old knows. We invite you to join our conversation in efforts to build the 21st century's new trade routes of language and music on a radically large scale across all our regions. Thank you.
I'm happy to chat with you also, not only with the video. Next.
So good afternoon. I don't have a video, so I will talk physically, okay, and in real time. And so I would like to talk about my research. Actually, my research is multimedia wireless networking. And my focus is on unleashing the impact through technology transfer. So I will talk briefly on that, how I approach this impact through technology transfer. So a brief word about academic history, so probably you know where I come from and where I'm heading to, right? So first of all, as a PhD student, you have an academic father, which is your advisor. And your academic father has also have an advisor, which is your academic grandfather. So, yeah, so my academic grandfather is Klein Rock. For those who have been using internet, you have to know this guy because he graduated from MIT and he analyzed the first internet and he helped to develop the first internet, which is evolving to today's internet. So Klein Rock has a student at UCLA called Tobaji. And Tobaji graduated from UCLA. He's working on CSMA. For those who don't know what is CSMA, CSMA actually is used in Ethernet nowadays. So Tobaji worked with Klein Rock, developed CSMA, and that became a standard in nowadays our Ethernet. So Tobaji subsequently went to Stanford, and so I followed him. So I basically worked with him on multimedia streaming. So besides that, I also have an undergraduate thesis advisor, Professor Kobayashi. And Professor Kobayashi actually working on signal processing. He developed what we call pulse response maximum likelihood coding, PRML. For those who don't know what it is, actually it is being used in magnetic recording nowadays. So in order to squeeze more bits into a magnetic disk, actually you can use that coding. It has been used everywhere nowadays. So I basically follow these giants, and now I basically now at UST, right, working on these various research aspects. So my research actually is to turning my work to commercialization. To do that, I basically work with three parties. Right? The first one is the government. The government provides me funding in terms of industrial matched grants, and also university, like the departments and the tech transfer center, provide me with some seed fundings and also advice on contractual agreement so that I can work with the industry. And the industry gave me also funding so that I can work on systems so that to effect this tech transfer. So I built technology in university, eventually, subsequently adopted by industry. So that is my goal, and so far I have been doing that, and I would say with little success. Okay. So my research goal is to build advanced network system driven by research innovations, designed by engineering excellence. So I work with an engineering team. Actually, I have like 20 to 30 members now. Most of them are engineers. About 10 of them are researchers. And we build innovative systems based on enabling technologies, leading to hopefully disruptive or killing applications. We build profitable companies, and we build our better tomorrow now. Okay? So I address the curse of scale. So every time when you have a small system, it works, but when you scale up, it breaks, right? So we basically address the curse of scale. What if the system scale up? What will happen, right? And how to address that. So I treat the university as my garage so as to prove the concept, not only just prototype the system, but to make it work in its actual deployment. So my first project, my ongoing project is on Streamfony, which is a network software for internet video streaming, which has been which I've been working on since my PhD years. And so basically, I designed the live and on-demand video streaming applications, and that has been going on since I have been here. So my second project is on Verami, which is actually an indoor positioning and tracking. If you are at HKUST, you can download the apps called Verami HKUST, where you can help to navigate the indoor space of HKUST. And the commercialization also has started. I basically co-found a company on that. And another project is on Lavinet, which is a Wi-Fi project. So I built design a router which can be put anywhere that offer you a very high performance throughput and adaptivity, ease of maintenance and all that. So these are the three projects I'm working on, and actually that basically form the three startups I have co-founded. And so indoor positioning, multimedia streaming, and Wi-Fi routers. And actually I also work in their junction. So for indoor positioning and multimedia streaming, we are looking at location-based streaming. For Wi-Fi routers and positioning, we look at designing our routers which can track people around. And finally is multimedia streaming and Wi-Fi router, we look at wireless streaming. So I look at all these junctions, and finally your unified network, unifying everything so that we can have a smart city. So briefly talk about this. Okay, so we have a research extreme here, work on these theoretical problems. But in practice, there is a lot of consideration which may be very difficult to address. So I am here basically bridging this gap, closing the feedback loop. So my team is doing that. Okay, so if you have any questions regarding that, I welcome you to talk to me, especially if you're interested in system research. So I will be very happy to sort of discuss with you and explore with you. Thank you.
Oh, we're using the mic? Haven't figured that out. Okay. Can you hear me without the mic? Yeah. Okay. I hate mics. Where's the, is there a clicker here? Okay, computer science is a really interesting discipline. It spans everything from engineering down to theoretical mathematics. Practical engineering is to very theoretical mathematics, and as you can tell from my title, I'm all the way on the other end of the spectrum as the others who spoke already. I don't also, the other thing about not work application. Used in most and just a little bit difficult for me to work on because I found some topics, graph algorithms, a lot on improving dynamic theory. Probably only have give you a little bit of a taste of what I do. It's probably only the first two things. There's only time for that. So, graph. If you're a computer science grad student, you've seen a graph. It's a picture, nodes, edges, and they're really important because they model problems. Lots of problems in looks down into it. What he's learning is in a graph. Lots of things can be modeled with graphs, and once you abstract the problem out into a graph, you're able to solve at least that version of the problem, the first version of the problem, without knowing about the original problem, using tools that already exist. I think that was said by Wigner for physical science. This is mathematics or physical sciences, but it's really mathematics is unreasonably effective in modeling many of the things. I've been working lots of the past year and a half evacuation protocols. That is, fire! Everybody has to run out. We've got rooms, hallways, and know how to get everybody out of the building to evacuate them out of the building. This problem was given to me by friends of mine in an architect. Started getting a lot of requests from the Japanese government after Fukushima to design evacuation protocols. The best way to do it was via graphs. So what you've got is you've got a graph. Think of the vertices as rooms. Think of the edges as being hallways. People you know in the rooms. You've got a problem with the hallways because the hallways have time that it takes to get through the hallways, but they also have width. You can fit more than 3 people into a hallway that's very narrow. And so the capacity of an edge is going to be the width of the hallway. And now you've got this idea that if too many people are waiting at a vertex in a room, they have to get out. Other people come to that room, they have to wait until the people there already have to get out. You have a lot of congestion. The issue that you need to deal with is trying to figure out a way, given a problem like this, to figure out the evacuation routes. The red nodes are where you're going to, and you have to figure out where to choose the route, how to choose the routes to get everybody out as quickly as possible. And this models certain type of protocols in packet routing as well. The problem is, of course, many of these graph algorithms we have are NP hard. There's no way in the world we're going to solve them. So what you need to do is solve them for special cases, solve them for probabilistic data, and try to solve them approximately. And these are all the things I've been working on with these problems. Okay, data structures. Second thing I work on. Well, data structures. And sound really has impact on going to be. And one thing that goes on over here is that you have to worry about your platform. What's useful in cloud computing, what's useful not work in a sensor node. You need a totally different type of data structure. And so the work I've been doing recently is building good search trees, I think. Solve it, unfortunately, it's an algorithm, so it's more of an intellectual exercise. And when you get a solution like that, you go and you say, okay, get something that's almost very cool. Also work in geometry. I won't go into the details there because I'm down to 10 seconds. But the idea is a lot of data can be modeled using random data, multidimensional data. If you know the properties of that multidimensional data, you know how fast your algorithm is. That's it. Thank you very much. And I think I'm at 5, right?
Okay, so good afternoon. So I will tell you a little bit what I and my group members are doing in recent years. So I'm basically a networking people. So whatever technology related to wireless networking, internet-based networking, mobile computing, those are the things that our group have interest. So all the people are talking about some fancy fields like cloud computing, Internet of Things. Eventually, I will be talking about big data. So what we did is as a basic infrastructure. Everything you want to talk about those fancy words, you need to be able to support the connectivity. So people are talking about using Wi-Fi, using 4G, using like all various type of wearable sensors. And some people even talking about using your visual light for the communication. So we are trying to make those communication experience better. How can you make your communication seamlessly and faster? So I'll just talk about two examples. One is what we are working recently to trying to enhance the performance for the next version of or next generation Wi-Fi network. What we are facing nowadays is our Wi-Fi become more dense and denser. The reason is more and more people are interested in using Wi-Fi, and in those like major press release, you will find it's difficult to access Wi-Fi because of the contention. Wireless communication by nature is everybody share the resource, so we are limited in terms of spectrum resource, we are limited in terms of the time resource. So we are actually working on various aspects trying to improve Wi-Fi's performance. Just give you some example. So suppose you are walking, your access Wi-Fi and then watching videos. Suddenly you are suffer from the performance. You have no idea what had happened actually because of your neighborhood and other people start using Wi-Fi, cause interference and cause you suffer your own like kind of experience. So for kind of this actually bring a lot of trouble for the user. So what we're trying to do is trying to change the architecture because Wi-Fi by nature is a distributed architecture. We want to add some like a coordination on top of it so as to make the performance better. So how can we make it? A lot of details, okay? And this is just one example, and then we are working on various aspects to further enhance the performance. For example, when you are talking, when you are sitting in the room, there are multiple users serving by the same access point. So that's why there will be multiple transmission happen, which cause a lot of contention. Well, instead of having multiple transmissions to serve multiple users, how about we just use one transmission to support multiple users in a single transmission, which can significantly reduce the contention probability. Well, there are a lot of challenges and issues, but we successfully made it and make our performance much better. Well, the similar ideas, we can use a lot of examples to demonstrate. The last one I want to use here is that we'll have more and more devices, wearables, etc., etc. And we have more and more wireless spectrum to access, which cause a lot of like contention. And because of the heterogeneous spectrum usage, there are a lot of contention and inefficiency happen. So we are trying to make the coordination better by having the per frame adaptation so as we can have better usage for our spectrum. So all in all, we are trying to make our wireless performance better so that when users enjoy their wireless access, they are having a better experience. I will use another example to demonstrate how we can make our communication experience better. We are trying to leverage our visual light. And again, because we are having the indoor environment, people are talking about wireless is too crowded. Can we leverage other resources? So people are talking about leverage visual light for your communication. And the reason we don't need to list why this is important, because it's green, because it's interference-free, because the infrastructure is there already. But to make the visual light communication is not that easy. The reason is to make the visual light communication enable, you have to do the modulation. And modulation basing on the light intensity, which causes user experience quite bad. if you cannot modulate the light intensity in a very high frequency, you will cause this flickering effect, so which causes a lot of cost. And so we come out a very cute idea by leveraging the modulation and then modulate the modulate to so as for the end user to enable your visual light communication and positioning. I'll just leave those details for open discussion if you are interested in it. So the basic idea is we can enable this much more flexible localization, just leverage your visual light. Okay, thank you.
Okay, I hope I know how to use this. Okay, my main research interest is computer graphics, but today I will talk about my more recent research interest, which is on user interfaces and interaction techniques. So I will skip all the methodology details and just show you mainly the results. Okay. So the first project is on multi-touch gestures for manipulating 3D objects. Okay. So specifically for rotating and scaling an object along with respect to an axis. Okay. So, yeah. So our goal is to design, simple gestures that involve only 2 touch points, just like in the case of using 2 touch points to manipulate 2D images, okay, and rotating it. Okay, so yeah. So the user interface have to automatically interpret the desired transformations based on the movement of the 2 touch points only. We also introduce some other intuitive gesture, such as snapping, that involves only drawing a curve. Okay, so I'm going to show you a demo of how to construct this the dog model. Okay, using our touch gestures. So we can see that the user can seamlessly use different gesture and to perform different transformation one after another, okay, without having to switch modes. Okay, the next project is on selection of graphics element. Okay, so the objective is that based on only a rough scribble by the user, our user interface can automatically review the user's intention of what he or she would like to select. Okay, such user interface is especially suitable for touch devices, which is tolerant to imprecise input. So this video shows the problem of traditional click interface. Okay. So as you can see from these examples, the shape of the scribble plays different roles in different scenarios. So our challenge is to design a solution that is general, that can handle all these cases. Okay. And also, we want a general method that is applicable to selection of different types of shape elements. For example, segmented 3D models. Okay. So here is a demo of our interface. So this software is available for download from our project page. It can be used to select segmented 3D models as well. Yeah, I'll skip the rest. Okay, so I'll show you the next project, which is on arrangement tools. Okay, so here to align the elements, we select the elements and then just issue the top align command. Okay. But if the elements exhibit a 2D pattern, such as this, okay, then undesirable results, you can obtain undesirable results using traditional command. So, in other words, traditional commands is oblivious to the groups. Okay, so in order to align them, individual group has to be selected explicitly. And sometimes in some scenario, it is ambiguous. Okay, which one would be a good alignment? So, so this is one possible alignment, and then we can also use by using different push pins, you can change the anchor element, okay, to be 1 or 2. Okay, so here is a demo of examples. Okay, so I'll end here.
Okay, so as I was sitting in my chair waiting to talk to you, a lot of thoughts were crossing through my mind. Who am I to be talking to all these people about psychology-related research? Who am I to stand here and talk about all these issues? But then I pulled myself together and then walked in front of you and I'm able to talk. Because I have a built-in mechanism that tells me that, look, it's okay. You can talk about this because you know enough. And you are able to articulate your problem very well. And so that gives me the strength to stand in front of you and talk about this topic. But the problem with automatic negative thoughts, so the thoughts that crossed my mind as I was sitting there are automatic negative thoughts. I had no control over those thoughts passing through my mind. They were just passing in and creating a commotion in my body, and which could have easily derailed me from standing in front of you and talking to you like this. What happens if you are suffering from mental illness? If such thoughts occur in your mind, very often they can spiral out of control and then land you into a lot of trouble, a lot of problems. So you can easily end up with a situation where automatic negative thoughts become the bane of your daily existence. It basically saps out your energy and makes you dysfunctional. Think about depression, think about anxiety, think about social anxiety disorder, think about the fact that people have difficulty standing in front of groups of people and talking. All these arise because of a root cause, which is automatic negative thoughts. Daniel Amen, who is a very world-renowned psychologist, proposed this theory called the ANT theory, automatic negative thoughts theory. So the basic idea behind this is that these negative thoughts quickly spiral out of control and leave you completely disabled to be able to function normally. So that's the whole idea behind the automatic negative thought theory. Now, one way of combating these automatic negative thoughts is that when you get these thoughts into your mind, if you have a built-in mechanism that questions these thoughts, that tries to challenge these thoughts, and come up with a mechanism to say, look, these are not reality. These are not the ones that should be causing me these problems. Then you will be able to overcome these and go on to function normally. This kind of challenges is what cognitive behavioral therapy teaches when you go to a psychologist. I'm beginning to sound like a psychologist. And you're wondering, what is a computer science guy doing with psychology? Well, it so happens that psychology is my other most favorite subject. other than computer science. And this sort of brought the two things together and helped me to design a project that brings my fascination with mobile technology together with my fascination with psychology, to bring together to come up with a solution to problems, mental health problems. So this is where we started out designing a mobile application. So the idea behind this mobile application was that if you encounter a negative thought, then you will be able to record these thoughts. Then you can go through a set of challenging questions against these thoughts, be it prompted by a system behind the scenes so that it may ask you questions and then you keep answering these questions. At the end of this conversation, you come to understand that you can solve these problems very easily. So that's the thought recording and conflict resolution process which my mobile app is aimed to incorporate. Now, behind the scenes, we also need big data analytics because you're collecting a lot of data from different users that can be input into the system. And when you analyze, you will be able to identify patterns. You will be able to come up with solutions to address the problems that people face in their life. So that's the big data issue that comes in behind the scenes. And this is where I am collaborating with psychologists to come up with the proper mechanism to address this. So we have a backend system that we are thinking of building to address. So there is a technical component and there is also the psychology component to this problem. Thank you very much.
Good afternoon, everyone. I'm a new member here. I just joined the department a few weeks ago. So today I'm going to talk about some of the challenges and opportunities in big data systems. So nowadays, we are all surrounded by a lot of data. So these data could be generated by some scientific experiments, such as this Large Hadron Collider, which may generate 40 terabytes data per second. And it may also came from some advanced devices like these Boeing jet engines, which also generate a huge amount of data every 30 seconds. And also some of the very large IT companies like Yahoo, it hosts one of the world's largest computer clusters with a massive amount of data. And also Amazon, you may not know that it has to process millions of requests every second, even 2 years ago. And let alone Google, we all know that it's very big, but you may not know, even 3 years ago, it has to scan through tens of billions of web pages every day. So now when I'm taking a look at all these numbers, that actually reminds me a famous quote by a great man. He said, 640K ought to be enough for anybody. That sweet old days have long gone. All right. So now the problem facing us is, given such a massive amount of data, how can we manage and process these data quickly and efficiently so that we can extract useful information without any delays? So first of all, we need some computing infrastructure to process such a massive amount of data. And that can be achieved by putting a large number of servers into a cluster. We call it cloud data center. So in terms of the number of servers, just to give you some examples, like some of the leading IT companies like Google and Microsoft, they have already millions of servers together. And the other leading companies, they also have close to 1 million servers. So of course, when you are coming up with a system at such a large scale, then doing some operations and management on top of that is much more challenging than the old days. Say 70 years ago, there's only a world market for maybe 5 computers. Okay, so definitely things has changed a lot. So now this thing facing us is we have the computing powers. We have the powerhouses. So how can we program on top of this massive big data systems? Okay, how can we do that? Well, although it sounds like a very formidable jobs, but basic intuitions and objectives is very simple. So all we want is we want to make this massive data center just as a single computer. So as an analogy, when you have a single computer, it could be a laptop, it could be a desktop, we have some operating systems on top of that. And then we can build up many useful applications of softwares on top of that OS. And similar things also happens in cloud data centers. We may have the cloud operating systems, or we call it big data systems, like Hadoop, like Spark. And based on that, we may build up many useful big data applications, such as web search, social networks, and other machine learning algorithms on top of that. Okay, so as you can imagine, building systems on top of this very large-scale systems, of course, may have a lot of challenges, but that may also give us a lot of opportunities as well. For example, we may have very limited network bandwidth. The opportunity here is we may try to design some new network topologies, giving us full bisection bandwidth. And also, you may expect a diverse workload, and that requires a general purpose big data processing engine. And also, the faults, and no matter it is hardware faults or software faults, may not be an exception. It could be quite normal, so that requires some fault-tolerant systems. And also, managing such large systems, you may end up with poor utilization. This may caused by some inefficient resource management and scheduling algorithms. And of course, when you have hundreds of users sharing such a large amount of servers, you may end up with unpredictable quality of service as well. And that also give us new opportunities to do some of the fair sharing or with predictable service isolations on top of that. And that actually, the last two challenges are actually my current project. So basically, I'm working on designing an efficient resource management and scheduling algorithm to speed up the big data. So finally, I'm going to end up with my talk using a famous course that I loved. Simple things should be simple, and complex things should be possible. Thank you.
All right, so I will talk about three problems that I'm currently working with my students. So the first is geosocial networks for two sample papers you can see there. One is VLDB13, the other is STD15. You can download from my webpage. So the main idea here is that we propose general architectures for geosocial networks and study query processing for various types of queries. So for example, here we have the real places in Las Vegas. And this is a user of a geosocial network who is looking for a Mexican bar with alcohol. So the top one result is here because it's only 400 meters from the user. It has been visited by one of his friends, and the textual similarity of the description of the restaurant matches closely the query terms. So this is just a sample query. We have done several types of queries applicable to geosocial networks. Another topic that we have studied is geosocial ranking. So, for example, here assume that Q is a query point, and we are looking for the top one user. Top one here means the best user according to both proximity to the query point and connectivity. So, for example, somebody may say that V1 is the best user because he's very close to the query point, and he also has two friends near the query point. Somebody else may claim that V4 is the top one user. Although he's farther from the query point, he has many friends around the query point. And another may say that V3 is the best user because he has three friends near the query point that are closely related to each other. In other words, they have a lot of triangles. So in general, the top one user depends on the application, and we have proposed several ranking functions that cover all these cases. The second topic is multi-criteria graph partitioning. The idea here is that you have users and you want to partition the users of a social network into classes. So for example, assume that we have 3 events denoted as squares, and we want to assign each user to an event so that the users are assigned to events that are near the user, and also the users are assigned to the same events as their friends. So for example here, V4 will be assigned to event P1, although he is closer to event P2 because his friends V3 and V6 are also assigned to P1. So we have a paper in Sigmund this year where we solve this problem using a game theoretic approach. So the main idea here is that each user tries to minimize his own cost function, and the whole thing is reduced to a game and it reaches a Nash equilibrium. We also apply several optimizations and so on. And the last problem is on uncertain graphs. So in uncertain graphs, we have probabilities on the edges. So for example, here this graph has 3 users, and the probabilities on the edges may denote the probability that they are friends. So usually these graphs are interpreted according to possible world semantics, meaning from this uncertain graph you can derive 4 certain graphs, deterministic graphs, each with a certain probability. And the expected degree of a node is the sum of the adjacent probabilities. For example, the adjacent degree of node U1 is 1.2. So how can we answer common queries like shortest paths or nearest neighbors or in between a centrality on uncertain graphs? The exact answer requires materialization of all possible worlds, which is prohibitive because we are talking about graphs with millions of nodes. So basically what people have been doing is Monte Carlo sampling. So usually, let's say they take 1,000 samples, they process a query on each sample, and then they aggregate the results, which is extremely expensive. So what we did is we tried to generate a deterministic graph from the uncertain graph that captures the properties of the graph. And the properties that we try to capture is the expected degree and the n-click cardinality. So we found that this is very efficient and produces very accurate answers. So currently we work on a similar problem, which is sparsification of uncertain graphs. All right, thank you.
Okay, so I'll stand here to talk. First of all, my boss is sitting here. And second of all, I can see Dee and Lily clearly. Okay, so that will actually motivate a lot to give this talk, to complete the talk and on time. Okay, and here I spent 1 minute already. Okay. Well, motivation is important. I mean, everybody do things with some motivation, and what motivates people to do something? It is their interest. Okay, so that is why modeling interest is important. Okay, so I mean, a lot of people work for various internet company like Baidu, Google, and they're very interested in presenting the right advertisement to the users in order to make more money and so on. So it is there is a very clear motivation about learning what the user is interested in. But you can imagine that in life you actually you also rely on knowing somebody's interest, or you need to know what people are interested in. Okay, for example, before my son go to college, I keep asking him, what are you really interested in? Okay, you want to be a fireman or you want to be a doctor? Okay, so you have to know that. Okay, now that he's in college, I don't got to see him very often, so I keep asking him, what have you done lately? Okay, do you just go parties and you really attend the lectures and so on? And I would say that by the time that he's getting close to graduation, I will ask him, what do you want to do next? So there are a lot of questions, right? So we have a lot of students sitting here, and I'm sure that your parents would have asked you a question like that, right? No? Okay, so if your parents haven't asked you this question lately, you better give them a call tonight. Okay, because they may have forgotten to send you the next check or make the next deposit as well. So it is very important. Okay. Now, of course, we are on a computer science student, right? So we deal with internet. On internet, there are a lot of data. Okay, you cannot escape from being tracked. Okay, so the data that we can make use of are query that you issue, okay, a page that you have visited, and messages that you have posted, and of course, physically, the places that you have visited. So these are all very important and can be used to infer somebody's interest. Okay, there are many applications. Okay, and I'm just point to one because I work on search engine for many years. Okay, on the search engine, you ask queries. Okay, when the search engine returns a set of results to you, you click on this result. Okay, so you have query, the time, and the pages that you click on. And then you can combine all of these to infer the user's interest because, you cannot make the judgment just from the queries, right? Because the queries are usually very short and very ambiguous. So what we have done here is that a lot of people kind of based on the page click and try to find out what pages the users are interested in and what pages that the user are less interested in. Okay, so the work we have done here is to use concept mining to actually understand what topics the users are interested in, okay, rather than just pages. Okay, from the topics and concept, we can do a more detailed separation to actually identify certain name entities, for example, the locations, okay, because, I hate to see Lily. Okay. And because of the location actually changes somebody's engagement. And from search to social network, right? Because on a social network, there would be social influence. A lot of people, people sitting next to you would have influence in your behavior and so on. So I go faster. And you can see that in order to extend a very simple concept of modern interest to more and more complicated application, you actually need to understand what does it mean by an interest. Okay, so we need to have some deeper understanding of interest. For example, whether interest is short-term, long-term, periodic, ad hoc, serendipitous, and so on and so forth. So you can determine the type, and from the type you can make more accurate inference on the actions that they would be doing. Okay, so all of these, text mining, concept mining, and machine learning. So I'm not going to talk about that, but just present you a few questions to think about tonight. Okay, in addition to making that phone call to your parents. Okay, how to define an interest? Okay, it is not so easy. Okay, so okay, I don't have time to do the story. Now, how is an interest developed? How does a person's interest affect his or her behavior? How does a person's experience affect his or her behavior, and hence their engagement? Okay, and of course, finally, how are we going to apply the knowledge, to build better applications? Okay, thank you very much.
Hello, my name is Sung Kim, and in our group, we are doing software engineering research. So basic idea is that we try to help developers. So usually developers spend a lot of time to make something work, and then they cannot go home in time, right? Usually they have a really long working hour or something. So really our goal is that we want to free these developers and then make them really happy. So today I'm going to introduce one of the work that we are doing with the students, Fuxiang Chen in here. So how many of you are still writing software? We are writing software, right? How many of you are really visiting this web page? Actually, I also visit almost every day because I search something in Google. always they actually bring me to there, right? So why this site is great? Because always some guy asks some questions, and then this question or this problem is not only his problem, right? We all have similar problems. So once we identified all same questions that I must ask, and then we can identify the solutions there, right? It's very, very useful. But the problem is there are so many questions here, and then sometimes I don't know what to ask, right? My source code has had certain problems, maybe, but I don't know what to ask. So here, crowd debugging actually can help you in that situation. So the idea here is that we're gonna look at all this Stack Overflow especially. We look at these questions and answer, and then especially a lot of questions and answer has a code pair. So he's saying that, oh, my code has certain problems. Why my code is so slow? Can you identify some problems? And then smart guy, like you, go there and then fix these problems, right? So in the Stack Overflow, what they have is that the problematic code and then sort of solutions. So what we do is that we make an index using all these questions, and then using this index, we search your code if your code has similar problems. And if your code has similar problems, we report you, right? We send you a very nice email. Hey, hello guys, we love your source code, but it seems like your source code is this kind of problem. Do you want to take a look? That's exactly what we are doing. And then here, we have a certain techniques that how we're gonna detect that. So it's one idea is that we're gonna use like very nice filtering. So we check the title is similar. I'm not gonna go into really details here. And this is another very smart technique to detecting similar code using code clone technique, and then identifying some terms, important terms. We identify what is important, what is not important automatically, and we can detect it. So using this, what we're gonna do is that once again, we send a very nice email to developers, including you guys, right? And then we check that if this technology is really working. So here, we select like many open source project, which is, I think, is very well maintained, right? So for example, Lucene, which is a search engine library, and then Log4j, they are really well maintained, right? And then we run this crowd debugging program on this source code, and then we identified this like many. So how many we identified? We identified 189 warnings. Using our database. It's amazing, right? And then, so how many of them really fix it? So we sent it to these nice emails to developers. In summary here, this number of confirmed bug is the bugs, actually they really want to fix it. 171 bugs are fixed. So the main reason is that because all these developers, they think they are very smart. So once we say, oh, do you want to fix this one? They're never gonna fix it, because they think my code is right. But because what we provide is that the Stack Overflow link with a lot of discussions. So this crowd knowledge can really help to fix them. So this tool is available for only UST students and PhD students here, right? If you have your source code, what you can do is that you can go to URL called crowd.debugging.xyz. So maybe if you have your computer, you can go there. And then basically you can type your email address because you want to send you an email. And then if you have a public Git SVN, you can send it. Or you don't want to use it, but you have a source code, you chip it, and then you can just post it. And then button, right? And then in 24 hours, you will send you an email, okay? Thanks a lot.
Enter question answer period. To any of the speakers, you can ask questions, but please tell us who you want to direct the questions to. Okay, anyone? Any takers? Yes. Please. Can we pass the microphone over there?
I think I can speak.
Okay, speak loudly, please. Okay.
So the question is for Professor Jogosh.
Okay. Jogesh.
Yeah.
Can you come here, please? Okay, please go ahead. Yeah.
So my question in
More questions? You must have questions. Yes, you can ask questions too. Okay. You have a question. Okay.
Oh yeah.
Okay.
Because I'm really trying to help developers, right? So you have a very nice way to handle this 3D object and 2D object or align them or something, right? And then do you think you saw the movie like Minority Report, right? So using these hands, they can manage all stuff. Do you think there's any way to program, like change the source code or do refactoring using these hand gestures or motions? Did you ever thought about that?
Yeah. What movie is that? I haven't watched that movie actually. Minority Report. Is it? No, I haven't watched it.
Object and you can change certain things. Doing programming. Using the motions. Do you think it's possible?
Using programming, no, I think you need some user interaction techniques. Yeah. So it.
Or changing body position. I don't know.
Yeah. I guess it depends on whether you want to whether the object, I don't know because I haven't seen the movie, whether the object is 3D. If it's 3D, you will need some 3D manipulation techniques that you need to manipulate it, all the degrees of freedom, including transformations and everything. Yeah. Or you want to align them, or you want to specifically arrange them to beautify the layout. So I think so you would need to design different user interface to interactively do it. Yeah.
Great, thank you. Okay. Yes, please go ahead.
So one question of the software helper, right? So you said that you actually discover possible warnings or mistakes in the source code. Is it possible to actually correct them based on the most voted answer of the crowd automatically without just suggesting a possible solution? Panos? Oh, really?
Debugging means not only identifying problem, right? Debugging is really fixing it. So because Stack Overflow has very nice P and P prime pairs, P is problematic, P prime is fixed. So currently we are working on automatic fix. And then probably we need your help. Okay, thanks a lot for the good suggestion.
Okay, any more? There's so many professors, they work so hard. Students? Okay, professors must be very clear. Now, so the next phase is we have some food outside, and oh, there's a question. Please raise your hand. Okay, yeah, go ahead.
We know each project might have their own language in their source code, but in Stack Overflow, maybe some people they maybe ask in their own languages, but this problem might be reused in the other languages. Maybe it's software pattern problem, and will the cloud debugging also be able to detect the same patterns if they're written in different languages, and based on that, given the appropriate recommendation?
Right, this is a really good question. So currently we are only focusing on Java and JavaScript, two languages we index that. But the question is that maybe can you identify similar problems in C? So this is very hard. This is very hard. And then probably we can identify certain very common error types like null point exception errors kind of thing. Maybe possible, but we haven't tried. I think it's a very good idea to try. But currently we don't know how to do it.
Very good. Any more? Okay, Wenya. Dimitris, okay.
I'm very sorry. I'm very interested in your uncertain graph. Yes, you have said that you may list all possible word, and then you determine which is the most possible. And I want to ask, if I have a lot of nodes in this graph, then there are many possibilities. Then how we can deal with this so many possibilities? Yes, because for my research, I also want to determine the possibility of the connection of the node in the uncertain graph. But there are too many nodes, like 100 million, so I cannot list all possibilities and then check which is the most possible. So have you ever encountered this problem? And how do you? Yes, I mean that if the loads in the graph is so many, and then there are too many possibilities. So then, how do you check which is the most word, the most possible word?
Approximates the uncertain graph. Do very efficient. We run experiments with 20 million. Generating deterministic very little time compared. Because if for some like in between centrality, you have to run all pairs or paths. So even one generating certain graph, but maybe we can talk about it after because it's complicated to answer. But in general, the algorithms are fast enough to run for 30 million nodes.
Very good. Okay, there's a question at the back.
Okay, thank you. I have a question for Professor Kim. Okay, thank you. well, I have a question is that how do you identify the bugs from Stack Overflow? I mean, from my experience is that often the posts on Stack Overflow ask about how to use this kind of classes, something like that. I mean, how do you identify bugs from Stack Overflow?
Right, it's a good question. So Stack Overflow has many different kind of questions. One kind is that, like she asked, right? So how can I use this library? How can I use these configurations? Or what's the best way to use something? But that's one kind, certain kinds. And another very also popular kind is that they want to ask other people debug their code. So they post my code, right? And then say, oh, what is wrong? My program is keep crashing. Or this program is really slow. Or am I using this library right? They're going to provide the code. And then the other developers, they look at this code, and then they're going to give some answers. Oh, this is right, wrong. This is right. And then they're going to post their solutions. And then this solution is good. Only if it's good, people mark it as an answer, right? And then we actually carefully look at these answers, and then the scores of these answers, and then we collect them. Using this database, we can identify similar errors.
You automatically pick the...
Exactly. We automatically identify types of questions. We automatically collect them. This is fully automated. There are many. We collected like more than 300,000 questions like that.
Okay. Thank you.
Okay, thanks.
Any other questions? Microphone is coming.
So I've got a question for you, Professor Kai. What's the difference between translating languages between languages and translating music and languages. So what's the most significant difference between these two tasks?
So it's a really interesting question. So one of the things that I think is really important for us to think about, because we don't normally think about it, is that all of our ideas, all of our thoughts, all of our perceptions, they're all represented somehow in our brains. Okay, somehow there is a representation, and that is a representation language. It might be feature vectors, it might be all sorts of, it could be logical propositions. There's many, many different kinds of languages that you can use to represent something. Music, specifically, to answer your question, is a sequence. They're also sequential languages. So instead of sequences of words, as you have in lyrics, you also have sequences of pitches. That makes a melody. You have sequences of chords. That's a chord progression or a cadence. You have sequences that are bass lines. You have sequences of grooves, which are sequences of percussive hits. So all of these are actually fundamentally languages as well. And the interesting thing is, evolutionarily, language was built on music. Our ancestors, they were singing before they were talking. And this was a lot of the scaffolding that our language abilities used, that adapted to build what became this ability for us to think abstract thoughts. Right? We are a pathetic species. We don't run faster. We don't smell better. We don't see sharper. We don't swim, climb. We would basically be dead as a species if we were not able to have this language ability to think abstract thoughts. Language and music, it's the only thing that we do better than other species. When we do, if you do functional MRI studies on the brain, or EEG, you discover that 90% of the processing that we do is using the same neurobiological structures for language and for music. And that's the only thing that differentiates us from all other species. It's really the same kind of processing, and it's subject to the same computational complexity constraints for learning and for live use, for interpretation and creation.
So do you mean that the music is a lower level of abstraction of the language, and we can extract the language meaning from the music?
Good question. It's not so much that it's lower level or higher level. It's very hard to put these things on a hierarchical scale. Many aspects of language were built upon primitive musical abilities for pitch and for meter, rhythm, and other things, both in terms of perception and in terms of generation. Right? There are birds who can sing, but they don't perceive the same way that we do, and vice versa. There are species that can perceive. A dog can understand simple things that you say to it, but it cannot produce it. Right? And so there are a lot of these capabilities that we've taken advantage of, but then we've further extended. And because our brains have evolved making use of language, they have evolved to be especially good at this, which then we turn around and we apply it in music again. And therefore, we've developed music that is much more sophisticated than what our ancestors started out with.
Okay. Thank you.
Okay, there is food and drink awaiting us. And let me tell you one last note. Some of you may have been wondering why I ran out of the room and back. There is, some of the faculty have spoken to you about the technology transfer, startup spirit, entrepreneurial spirit, and so forth like that. Several of us have done that sort of thing. There's a new student-led initiative called The Base, which is at LIFTS 29 and 30. If you haven't been there and you're interested in transferring technology all the way from the theory that we're talking about into actual, the world's first translation service or whatever, what Gary was talking about, that sort of thing, then do introduce yourself over there. It's a very comfortable environment with ping pong tables and whiteboards and bean bags on the floor. It's really a lot of fun. I had to do that because I'm one of the representatives on the university's entrepreneurship council or committee, coordinating, I don't know, something like that, the steering committee. And I think it's a very nice thing for you at this stage to be thinking about how does the theory that I'm working on potentially translate into actual impact in the real world. So do introduce yourself there as well. Okay, wonderful. I'd like to thank all of the faculty for their 5-minute inspirational talks and you guys for listening again.